Wait till I give it a fresh coat of paint, tune up the engine a little. I'm gonna be the next drag race champion. Oh shoot, my bad. Sorry, I was just practicing my lines. That's my bad, gang. Anyways, where were we? Yes, the existence of eigenvalues. So, in the last episode, as a little recap, we talked about polynomial operators, and so we're gonna see why they're so brilliant in this video. And so just as a reminder of what we've actually done even further back, we talked about a condition for an eigenvalue being an eigenvalue, if that makes any sense. What I mean is, remember, by definition, for something to be an eigenvalue, we need it to satisfy the following. So we have some non-zero vector v, right? I guess oftentimes you see this in the reverse order. You have this eigenvector, right? Which has the property that it gets scaled when it gets multiplied by some operator t, right? And then this thing that it gets scaled by is just the eigenvalue of that non-zero vector v, that eigenvector. And so we did some rearranging and we came to the conclusion that in order for lambda to be this eigenvector or eigenvalue, right, we need the following: the null space of t minus lambda I. We need this to not be equal to this trivial 0, right? Because if it is just this trivial 0, then TV, then this, I'm just gonna end up proving it again. That's probably what I'm gonna end up doing. But if we apply this to some vector v, right? Okay, this is v, this little equation here means v is in the null space of t minus lambda I, right? And if v, if we were to distribute v through here and then rearrange, like bring this to the other side, we get tv equals lambda v, which is the same condition as we usually have for eigenvalues, right? But anyway, if we have this, right, and v is just 0, then we lose that condition. It's not an eigenvector anymore, and so lambda is therefore not an eigenvalue. So this was our condition, right? But we need something a little better than that, because this doesn't really talk about existence. Like, just because we have this we can't be like, okay, if I have some vector space, like, do I have an eigenvalue? Like, does one exist? And that's what we're gonna really touch on in this video. So let's see. I'm gonna get rid of all of this. So when does an eigenvalue exist? Well, I claim that if we have a vector space, okay, just some vector space v, okay, and then take any operator on it, and in fact, it's crucial that v is finite dimensional, okay? And we're actually going to see a counterexample if we assume v is not finite dimensional. If we take an infinite dimensional space, then we actually can find a vector space and a linear map t such that t has no eigenvalues, okay? But here we're going to assume v is finite dimensional, and usually we're interested in finite dimensional vector spaces in the first place. So this is not too bad of a condition to make, okay? And then, okay, so t is some linear operator on v, all right? And then I claim this is all I need. Oh, and then also our field that we're endowing this on is complex numbers. Then I claim t has an eigenvalue, okay? That's our claim. So I'm gonna box that bad boy up. Okay. Great. So, how do we prove this? Well, it's actually a very, very beautiful proof. And this initial step, I don't know who came up with it, but they're absolutely brilliant. They're Einstein, okay? Or Isaac Newton, whoever you think is smarter. But I digress. So, I'm trying to think of a motivation to explain this first step, but I think I'll just let the elegance speak for itself, okay? So we're gonna assume that the dimension of v, this is where our assumption comes in, that v is finite dimensional. The dimension of v is some n, okay? Where n is, you know, some positive integer, okay? That's using this condition that v is finite dimensional, right? okay, so theoretically then, if we create a list of n plus 1 vectors, they can't be linearly independent, right? Because if they were, then we'd be sort of violating this fact that the dimension of the space is n, because we found a subspace that has dimension greater than n, in particular n plus 1. So, okay, let's use that. Well, how do we find n plus 1 vectors? What if we just apply t to some vector v, n times, and then take v itself? So let's look at this set of vectors. So we're looking at v and then tv, t squared v, all the way to tn v. Okay, I think you can agree that there's n, vectors here, right? We have v itself, and by the way, v is non-zero. Okay, so we've taken some kind of v in v, right? And one exists, right? It's a vector space, it's not empty. Okay, so v, tv, blah, blah, blah. This has n plus 1. Oh, these colors are atrocious. This has n plus 1 elements, right? Okay. Well, it has n plus 1 elements. What can we do with that? Like I just said, they have to be then linearly dependent. So what does that mean? That means there exists, C1 up to C, or I'm going to say C0 up to Cn in our C, right? Because we're dealing with complex numbers as our field, such that, well, we have the following. We have C naught V plus C1 TV plus dot 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 plus Cn Tn V equals 0, where these aren't all 0. Okay, one concern here is, actually I'll get to that in a second, all right? But okay, what we have here, right? Let's factor out that v, because there's a v in every term. So I'm gonna bring that v out. Just to, by the way, again, at least one of these has to be non-zero. Like we can't have z0, z1 equals 0, z equals cn equals 0. We can't have that, okay? Because, these are linearly dependent. They're not independent. That would imply that they're independent if they're all 0. So I'm gonna factor that v out. So we have C0, I'm gonna put our little identity there, okay? And then we have C1t plus dot 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 plus Cn t to the n, and then v equals 0. Okay, so if we define this to be our little polynomial then, we just talked about polynomials, let's put them to use, right? This looks like a heck of a polynomial, right? It has degree n, it seems, okay? Unless that Cn's 0. We don't know it has degree n actually, because Cn could be 0, okay? Okay, but we're gonna preemptively call this PT, but we might change that in a second, okay? I'm gonna warn you. But what we now know is that we have some kind of polynomial thing, okay? Such that if we apply v to it, it equals 0. Okay, but what do we know about polynomials and zeros? If you remember the fundamental theorem of algebra, if you don't, I would recommend searching that up. That's very important here. But this is the beautiful thing, all right? We're reeling in the fundamental theorem of algebra in a discussion about eigenvectors and eigenvalues. I mean, are you serious? I mean, math just doesn't get any better than this, okay? So what we're doing is, if this applied to v is 0, okay, then that means this polynomial has at least one root, okay? Well, I should say the polynomial applied to v here has at least one root. But what do we know about the polynomial? Since we're dealing with c, we know that, remember, if you read about the fundamental theorem of algebra, you take some kind of polynomial, say p of z, it can be written as some, let's say you have some constant there, right? And then z minus your first root, I'm going to call r1, times z minus r2, blah, blah, blah. If this has, let's say, degree n, okay, so p of z, degree n, then you go on till z minus rn. It has exactly n roots when we're looking at complex numbers, okay? Sometimes people write it as, in parts, right? So they say the first part of the fundamental theorem of algebra is that every polynomial has at least one complex root, okay? But the second part, then they say, is if you look at polynomial over complex numbers, then it has exactly n roots, okay? So all we really need is that first part, actually. I mean, it follows from this, right? So this has, P of t, then has at least one root. Now, I'll get to that, because there's technically an assumption we need to make on P of t, but I digress. We'll come across it when we need to. What are we at? We're at 10 minutes. Okay, great. I think we might split this into two halves just to sort of edge, my bad, just to edge the beauty of this result. Okay, so P of t, but when can we apply this? This doesn't make any sense if P has 0 degree, right? Because if P has degree 0, then it's just a constant. We can't factor anything out, okay? We want to factor something out, because once we factor it out, we get something that looks like t minus, let's say lambda. We're going to call it lambda, okay? T minus, well, if you just look at that, okay? And you sub in t, right? Using our little identity thing, we get t minus I times r1. Well, doesn't this look really suspiciously similar to when we were dealing with eigenvalues, right? We were looking at the null space of t minus lambda I. So if we just rewrite r1 as lambda, then we get that essentially, right? So we want to factor something out to approach that, okay? But what if there's nothing to factor out? How do we know that if we look at all of these guys, c0 plus c1 t dot 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 through cn t to the n, how do we know that that's not just a constant polynomial? Then this would all go to crap, okay? For lack of a better word. Well, we know that because let's say everything else was 0, okay? So leaving us with just a constant, just c0. Then we'd have c0 times v equals 0, then you divide the c0 on both sides, then you get v equals 0, which is a contradiction. So we know this is non-constant. That's important, okay? All right, so now in the next video, we're gonna sort of take it from here, all right? We're gonna go from this fact that we can factor this into one of these little roots, okay? So I'll see you in the next video. This is gonna be an exciting little journey.